Okay, so my name's Alex Duyck. I'm going to be presenting on the Meta Host Network Interface and the fbnic driver. So with that said, quick agenda. First question probably most of you have is why would Meta be building our own NIC? I'll go ahead and cover the Meta Host Networking Interface, current software development status, get a bit into detail on the fbnic driver and some of the features we enabled in the hardware, describe what comes next, and if we have time, I'll do a quick demo and along with a Q&A. So why build our own NIC? First and foremost, just so most of you know, this project started pretty much right at the start of COVID. So I don't know if many of you remember, there's this little thing called the supply chain where stuff's supposed to get through to get to us. Turns out a lot of things broke during that, including silicon and all of that. So led to a number of issues. One of the big things with us actually building our own NIC is the advantage is we have a much tighter control of the supply chain. Basically, we're the ones responsible for designing the silicon IP. Then we can actually farm it out to multiple vendors if we need to see if either they can fab the silicon for us or put together boards for us. So as a result, it gives us greater control of the supply chain and the total cost as we're able to work with multiple vendors to get the same product. For example, like I don't know how many of you remember the IDPF talk where it was, okay, we want all the vendors to go to this interface. It's kind of something similar to that, except for we already designed the interface. We just want some other silicon vendor to manufacture it for us. Another big reason for doing this is it actually gave us a much tighter control of the maintenance for our products. Previously, if we run into an issue, say we chase down an issue on a NIC and it gets into firmware, you're stuck waiting on the NIC vendor to come back with a firmware fix for you. I can say from past experience, I've actually been in a couple of companies where that actually killed a sales deal for us. So we had to find an alternate vendor or alternate product at that point in order to work around it because the vendor couldn't get us a fix fast enough to address the customer issue. In Facebook, it's something similar. What we end up running into is if we have systems going down for a firmware issue, we have very few options other than essentially just have to pull out the NICs, which you can't really do at that large of a scale and quickly replace them in many cases. In addition, one of the things we have, since we're the ones manufacturing the NIC, is we have ownership of the firmware. So when we run into this sort of issue, hopefully we can just go through and fix it ourselves. And in addition, we also have access to the internals of the hardware. So when we do see an issue, we can actually go back to simulation if we need to and try to verify, okay, is this something that's going on in the hardware and get an accurate reproduction of it. The last main reason is actually the ability to innovate in areas we're interested in. More often than not, we have a lot of, okay, we want to really try this project, but then the problem is, okay, we need a NIC that actually does that. So, for example, with the HOMA presentation yesterday, you know, it's okay, we want to be able to offload this. Well, in order to actually be able to test something like that in hardware, you'd actually have to have hardware that can offload that. And trying to negotiate that with a vendor for a proof of concept isn't going to work out very well unless you're agreeing to, okay, we're going to buy X number of million beforehand. By having our own silicon, we can actually go ahead and maybe include a few proof of concepts for ourselves to work with. And then if we decide to not go that route, we can always drop them later. And one of the things that came up in a lot of the presentations I was shown back in the day when we started this, the expression owning our own destiny came up quite often. Essentially, it's the accumulation of all of this. It's if we make a decision, we can go forward with it, and we don't have to be told no by anyone else. It's our silicon, so we can make the decisions on what we're going to do with it. So, kind of summarize, so the Meta Host Networking Interface is our own foundational NIC designed by Meta for Meta. Basically, the feature set is based on our use cases, not any enterprise use cases or any other customers. It's specifically focused on our use cases. I was actually hired into the team back in October of 2020. To give you an idea of how things were going, I started boot camp, and about 2 weeks in, they handed me the spec and like, okay, look this over, tell us what you think, what do we need to add? We've got to start building on this as soon as possible. So I started October 2020. By the end of the first half of 2021, we already had a driver and a working QEMU simulation for just a single host. The following year, by the end of that year, we had an FPGA that was passing traffic, and we were using it to do internal testing for our own use cases, making sure that with a silicon setup, it would work closer to what we expected. From after that proved out, we started working on a multi-host NIC, and that we had taped out, I think it was sometime late 2022, or I'm trying to remember, no, maybe it was early 2020. Anyway, we had the first silicon in second half of 2023. We've been working on ramping it up and testing, and our plan is to basically start putting it into production next year. So one question that you might have is, what are some of Meta's use cases? So specifically, one of the big ones that jumped out to us that we discussed is the fact that we don't have virtualization necessarily in our data centers. For us, most things happen at either a container or a system level. And so for us, it's mostly containers. It's not so much VMs. In addition, we have almost no IPv4 in our network. There's not a whole lot of reason for us to be working on IPv4 offloads if we're not going to use them in our data center. Likewise, one of the use cases we have is for load balancing. We have a lot of IPv6 and IPv6 tunnels. So that needs to be something our hardware can go ahead and parse or handle on the transmit side. In addition, a lot of issues we had seen in the past, and actually something that had come up in, I think, my interview, was questions about how to deal with traffic isolation between functions. The way we're addressing this is we actually have it almost physically sliced off. Basically, we're sectioning off SerDes lanes for each function. In addition, we don't have any Wake on LAN support on this device. However, that said, we do have BMC support. So that's kind of a slight difference between us and other NICs, because most of them will have Wake on LAN, but not necessarily BMC. Another big focus for us is congestion avoidance. We have an entire team essentially that's working on monitoring traffic, making sure flows are going where they need to go, and they're not getting dropped off the network. And so anything we can do at the NIC level to actually participate in that is also useful. Another feature that we added was header data split. One of the initial use cases we had for that was actually something akin to what Eric's done with the 4K page flipping. But turns out there's another use case for that kind of bit us a bit, but I can go into more on that later. It can be used for something called device memory TCP. Basically, it's a way of allowing kind of bypassing the kernel for the data portion of a packet. And the other thing, like Kuba, I think mentioned earlier, we don't actually have jumbo frames through a good chunk of our data center. We've enabled it in a few spots, but it's not like, yeah. Anyway, so yeah, our average packet size is usually on the smaller side. It's usually like, I think, 500 or 700 bytes, somewhere in that range. But yeah, we're exploring jumbo frames. So in terms of where we're at for software.
Alex?
Yep.
One question. What MTUs are you supporting?
The NIC itself will support up to 9200. Actually, a little over that, if I remember right. So, but yeah. So in terms of where we're at for the software, at this point, we actually have an out-of-tree driver that has almost all the features complete. That's been our lead vehicle for development and iteration. And it's been going through ongoing tests on multiple platforms. One thing from actually our discussion in the driver workshop that occurred to me, as far as a development setup, out-of-tree driver ends up usually being the preferred way for us to go, just because then you can actually just put it on a stable kernel and it just works, and you can quickly iterate it. If you have a problem, you go on, fix a couple lines of code, rebuild the driver, test it. Okay, good. We're good to go there. We also have an in-kernel version that we're working with, which actually I'd submitted the first version of it back just after April 1st because I wanted to avoid someone thinking this was an April Fool's joke. But with that first iteration, we ran into a little bit of a snag. The full story on it at the link. Basically, was it A Tale of Two Troublesome Drivers, if I recall the title. Basically, it's us and firmware control, and there was a bit of contention there. But anyway, with that, the V5, which is what I submitted last Friday, so a week ago today, was actually accepted on Monday of this week. That driver is just a minimal driver. It can load link past traffic. It actually has no stats at all from what I recall. So it's a little bit confusing because you can't tell it's passing traffic, but stats is in an upcoming patch. With that, it should be included in the 6.11 kernel. And basically the in-kernel driver, the plan is we're going to use it in production. We just got to get enough of the functionality into the upstream so that we can then pull it in. And then until then, we're using the out-of-tree driver as a workaround. Some other bits. So sharing some of the Linux driver code, we also have a UEFI driver. That driver at this point is successfully provisioning systems. We haven't had too many issues with it. We've got a few, but it's mostly just like API issues because I haven't done a UEFI driver before, so I didn't quite know what the expectations were. A few other pieces to the software. We have an internal firmware team that's working on the firmware for that. I also dabble in the firmware here and there. Right now, the main role of the firmware is it sets up the data path for the BMC so it can talk to the outside world. And so ideally, when the driver comes up, we have a message that says, I'm taking ownership of the NIC. If you want to do anything, message me about it, essentially. But in the meantime, we're seeing a few issues. One of the roles of the firmware is also to act as a middleman for the I2C. And we're seeing I2C issues on that right now, which is actually causing a few problems. In addition, we had seen some Ethernet PHY issues. I think we've got most of it resolved. Because one issue is we're partially separated from the Ethernet PHY. Like we have access to it, but we don't know which registers are supposed to belong to us because they put two PHYs into one region. So unfortunately, we usually have to defer to the firmware to go ahead and update the correct region for us. Like I mentioned, the other big piece for us is we have a QEMU. Actually, we have 3 of them for all the bits and pieces. So we can essentially emulate most of a full system going from the host to the firmware to the BMC and then back out if we need to for handling most of the setup and data path or control path configuration. Data path, it's not going to do at any kind of real world speeds, but essentially they can all be interconnected to exercise any of the mailboxes between the two or messaging for NCSI, for instance, with the BMC. And the last piece is we've been working on a continuous integration, continuous deployment framework. A piece of that is called LNDT, or Linux Network Driver Test Framework, if I remember it, something like that. And Lee will be presenting on that later, so I'll leave it at that. So the fbnic driver itself. So what all did we pack into it? Essentially, by and large, the driver ended up being kind of a wish list for, okay, we want to do a simple driver. What features do we want to throw in? So we've got a few DevLink health reporters for monitoring the firmware. A debug FS, primarily just for dumping the internal NIC state in terms of tables and such, so we can get the descriptor rings, the TCAM state as far as the software is aware. Trying to think if there's anything else. Maybe some internal state, like I think there's a flag for BMC present if the firmware or if the driver thinks the BMC is enabled. In terms of the queue count, we did things a little bit differently. So we have 128 RX queues and 256 TX queues. The reason for doubling up the TX queues is we have one TX queue for XDP and one TX queue for regular transmit. So as far as the Netdev is concerned, it just has 128 TX and RX queues, but we actually have these additional queues there for the XDP transmit side. As far as the offloads, most of our offloads are focused on some sort of break it up generic. So we don't have a specific like IP checksum or IPv6 checksum offload. We just have hardware csum. We also have just a GSO partial offload. So essentially we support TCP, UDP, and I will partition everything except for the L4, and I'm just going to replicate those headers. So the assumption is GSO partial takes care of it for us, and we can just replicate everything at a certain point past where we mark in the header, in the metadata. Another big thing, as some of you that might have submitted more recent stuff know, Kuba is a big stickler for, okay, we have to do all of our allocations before we tear down the NIC and bring it back up again if we make any change. So all of our queue allocation is set up based around that model, so that when we go to change something like the channels or the ring size, basically we do all of our allocations down, up, and then we're just back off and running again. It's made for some interesting things because technically we double up in terms of the number of NAPI instances we have for a brief period there before we go ahead and cut the old one. So it's almost more of a RCU style allocate, replace, and delete. And then we get into the some of the other stuff. So we have separate page queues for, so this is the producer queues for header and payload within the RX path. So with our header data split, the header and data can come from completely different pools if we want to. Our setup ends up using a page pool with RX or with a fragment-based RX. So one of the things is our receive path, it pulls buffers in and it will just start chopping them up and give them back to us in chunks. When I show you some of the RX descriptors later, I can show you basically we get a page and an offset that we're working with, page offset size. So it just looks like your standard scatter gather list. It's breaking it up for us beforehand so that we can go ahead and get better use of the page instead of letting them get the buffers get interleaved and such. Anyway, the other thing that we've been looking at doing, so one of the features we had is what's called payload packing. That's basically, if we have a queue, we have the option of actually having it right tip to tail within the payloads. So for example, if we want to test something like try to get closer to hardware RSC without doing full hardware RSC, if we enable this mode, there's actually two different modes. One is it just packs everything. The other one is, well, if the RSS hash matches, then I'll go ahead and just pack these two frames together. And so the general idea there is we can go through and start doing some testing to see how much of, for example, the advantage of RSC is just it packing the frames versus it doing the actual manipulation to coalesce everything into one giant packet beforehand. And then another thing with that, our descriptor setup is a little bit different than some vendors. We actually have 4 different descriptor types on the RX completion side and on the TX producer side. The general idea is we want to try to keep things as small as possible for small packet workloads that aren't actually trying to make use of any advanced features. So for example, if we're only doing a 64-byte send with no other offloads, for TX, we can actually do it in technically one 8-byte descriptor. For the RX side, it would end up being 2, one for just the page and then one for the metadata. So it'd be a 16-byte descriptor. So we can actually keep the overall overhead on the descriptor rings quite small. And like I mentioned before, we're interested in congestion control. So we actually have support for reporting when we've exceeded a congestion threshold on our internal FIFOs via the RX descriptors. So if we start getting that, we have the option, and this is something I actually was using in the our FPGA stage. We had a 100 gig link and an FPGA that was doing like 40 gig. So with this, I was actually able to pull the metadata off the descriptor, ECN tag the frame, and so we could go back to back and we wouldn't actually be dropping frames because the explicit congestion notification would kick in and actually tell the sender to back off, and we could actually reach just about the full limit of the NIC without actually dropping frames. Likewise, on the transmit side, we support earliest departure time for the TX queues. So with that, we could end up taking a TSO frame, for instance, and slowing down how fast it's actually being sent out on the wire versus just having to reduce our window size if we're wanting to avoid overwhelming the receiver. And another thing in all the congestion stuff, one of the things that's been used is timestamping for congestion control. And with that, we had identified there was a few issues in the past where if you try to request more than one TX timestamp concurrently, more often than not, a lot of NICs would have problems with that where they just return an error or reject for the second one. So with our design, we actually went through and made sure we have the option of basically timestamping all the TX and RX packets, either incoming or outgoing, and our hardware actually fully supports that. So it basically has a queue it can feed us back on at least at the hardware level in terms of all the timestamps for the packets. And then we even went through and did some minor things. So for example, one of the things we did is we actually consolidated the right to enable the interrupts with the setting of the TX and RX interrupt moderation thresholds. So with that, we were able to actually go through and reduce it. So we essentially are only writing to give new packets to the RX path, notify the TX that it can go ahead and send, and then one write to set both interrupt moderation thresholds and re-enable the interrupt at the end. So question is, what comes next? So like I said, we have this big out-of-tree driver, and we have to have basically get a lot of the stuff converted over so we can get into the in-tree driver. So this is like a abbreviated list of a lot of the features that we have in the out-of-tree driver that haven't been ported over to the in-kernel driver yet. So yeah, I'm not going to read through all of it, but yeah, a lot of it. So like we have entire files that are missing yet. So we don't have the actually I didn't even list PTP in here, so that's missing entirely. Like the ETH tool file hasn't been added yet. The hardware mon, the debug FS, and one thing, yeah. So like I mentioned, the driver wasn't really, actually, I don't know if I mentioned that. Yeah, so the one thing that kind of snagged us up when we initially pushed the driver is I completely overlooked the fact that, yeah, we had control of most of the PCS and Mac path, which is a bit different than what you see on a lot of other vendor NICs, because they usually have firmware that's in front of that. So when I pushed it, Andrew pointed out, hey, you know, most of that stuff can go into FileLink. I'm like, what? And so after a little while looking at it, trying to get my head around all of it, it's like, yeah, we can actually support 2/3 of the path in FileLink, because we have a little bit that, so the Phi portion is buried behind the firmware, unfortunately, in our case. So I've got to go through and do some work on that. So we're going to be pushing a bunch of changes to FileLink in order to support CGMII, which is a 100 gig media independent interface, forward error correction, multi-lane support, bit error rate test, and loopback, at least at this point. So we'll have to see what else pops up. So we've had like the bit error rate test and loopback didn't come up until some conversations yesterday. So yeah, and then like I was mentioning, we have you know, the TX path. We haven't even pushed TSO yet, so we've got to get that implemented so we can actually start to show some better throughput on the TX side. So that's pretty much where we're at for the current generation. What about the next generation? Well, that's the thing, is we're kind of already starting to put together our wish list. So as a number of presentations have kind of shown, hardware GRO has some benefit. The only problem is hardware GRO for us has a history of being very painful, because up to this point, almost no one has gotten it right. There's always something that seems to go wrong, and it ends up having to get disabled by default. For that reason, one of the things we're looking at doing is trying to see if we can maybe come up with a hybrid that isn't a full hardware GRO where it starts taking away data from us. And to that extent, this is something I think I had mentioned to a couple people on a hallway track, like a Netdev or two ago. The general idea would be have the hardware, instead of it doing all the aggregation, it just gives us hints of, hey, this header and payload, here's the context for them. I'm going to track them going forward. If you want to accumulate them and put them all into one context, that's great. If you want to flush them, that's great. I'm not going to manipulate the frames, but if the software decides it wants to, here's a hint on what group these all belong in. Doing that, we should be able to, you know, if nothing else, we'll probably have that as a chicken bit feature where, okay, once our hardware GRO is found to be broken, we can roll back to this so we at least have some benefit. Likewise, one of the things we'll have to work on for Gen 2, and I apologize for not catching, I think MaxS KB frags came out, like, that change was about a year or two after we'd already started. But yeah, so we want to do jumbogram segmentation, so we're going to have to fix our NIC for the next generation so we can actually do MaxS KB frags more than 21. And with that, we should be able to then start working on sending, segmenting jumbograms and then receiving them as well. And like, as I mentioned, we have so the software side I'm still working on, but for the next generation hardware, we're going to want to try to push the firmware out of the way so that we can actually do the full Mac PCS Phi. And hopefully with that, we can get all of that into FileLink for the next generation. All that will be resolved. Another topic that's come up multiple times here is PSP. You know, security is becoming a more important thing, and PSP seems to be the way a lot of us big data center types are going about addressing it. And so we're going to be looking at trying to see if we can get that in for the next version of our NIC. And lastly, like I mentioned, we have containers in our data center, but we don't really have VMs. For that reason, we're starting to think, okay, maybe we need some virtualization solution. And looking at things, we thought SIOV would be the most obvious choice for this. The fact is, SIOV, the whole idea is you're composing something, which means if you're composing it by putting a bunch of stuff together, you can take that bunch of stuff apart and make use of it other ways. The general idea here would be, okay, maybe we look at having support for SIOV. Maybe we use the full thing, maybe we don't, but it should have enough components for us to be able to make use of that. For our container use cases, we can come up with some solution like sub devices or something along those lines if we need to at a minimum. So with that said, yeah, we got a lot of stuff going on. So I just thought I'd go ahead and plug. By the way, we're hiring. Yeah, I didn't bother with the table. I just figured, okay, I'll put one slide in. Okay, so with that said, we can go to demo and probably Q&A, and I'll probably do both at the same time. So, well, anyway, I was just gonna, so let's see. Which one is this? So this is the QEMU. But no, this is live. So like, for example, transmit descriptors, trying to read through this, like I've gotten used to reading all this. Basically, this T value here is the type. So everything in terms of the way our descriptors work, it always starts with a 0 and always ends with a 3. And then there's somewhere in the middle that's going to be optional. So what ends up happening here is the 0 is the transmit metadata, 2 is the header, or yeah, 2 is going to always end up being your payload with header. And you might have multiple 2s followed by a 3, indicating, okay, this is the last payload, essentially, for the TX. Then we have a 1 that could be put in between if we're doing a TX timestamp or other functionality, but we didn't implement any other functionality. The general idea was it'd be 0, 1, 1, 1, 1, 1 for any optional metadata we needed to pass, and 2, 2, 2, 2, 2 for the data, and 3 to close it out. And like I said, for the RX side, it's something similar. Fortunately for this, there's not, without header data split, or without going into jumbo frames, everything just fits in the header, so it kind of gets pretty boring. So 0 here ends up being the header for the type. 1 would be payload pages. 2 would be optional metadata, and 3 is just the final metadata. So kind of the RX and TX are just flipped versions of themselves. Yeah, wrong button. Let's see. Let's try to see if we got the other system still running. Yeah, so in terms of what we got right now, so that one was the QEMU instance, which actually I can just, so like I said, so one of the things we got, so like if I want to, in our builds, what we end up doing is we'll actually have a serial connection running from the NIC into the BMC. So via that, we could actually go in from the BMC and just fire up a serial console to go take a look at the firmware state. It just actually allows for a lot more debuggability. Let's see. And then likewise, like I mentioned, we can actually go in and take a look at what the software state for the TCAMs are via the debug FS right now, which this one, since it's the QEMU, I don't have the BMC enabled. So it ends up being a pretty simple setup. Most of these rules on the end are just there for RSS and such. So we can identify the bottom one ends up being Ethernet, IPv4, IPv6, IPv4, TCP, UDP, and same thing, V6. And then I can jump over to the actual hardware, and it's like, you know, I've heard several times now, single flow does about 30 gig. And so it's like, oh, I wonder how we do in terms of single flow. And it was like, okay, well, looks like we're doing about 36, 35, yeah, a little under 36, 35 to 37 gigs for single flow on our NIC. So it's like, okay, so we didn't screw up the RX path that bad, I guess. So anyway, with that, we can probably go to questions.
I'm curious, how did you implement EDT? Oh, really? Do you just like delay the whole TX queue, or do you have out of order
it ends up being the whole TX queue, if I'm not mistaken, I think. Yeah, it's I210 style. Yeah. Okay, yeah, so if that's the question, yeah. So otherwise, I'm like, okay, do I have to go pull up code now? It's like, I wasn't sure if you're talking about the driver or the hardware.
Yeah, so maybe like we will have to have some different name, because there are 2 ways to do EDT now, out of order versus stalling the queue. The I210 versus the way IDPF will enable it. So maybe, Eric, something we'll have to look into, because people are using the same term here. Okay, question is about, I didn't see flow steering. Are you guys not doing any of that anymore? Or?
Well, so that TCAM table I had, we have about like 50 empty entries in it. Yeah, otherwise we're not doing any flow steering.
About the hardware GRO, if you need tips, I've graded my hairs getting it right on IDPF and the IPU. So yeah, we can discuss that. Could you go back to your last slide? I think I had a question, and now I'm, yeah, SIOV. This is, you're looking at SIOV R1 or R2? Because the R2 spec is not ready, and
I think we're just looking at R1.
Standardized. Sorry?
I think we're just looking at R1, but like I said, for us, for our purposes, we're just looking at the components of it, essentially. We don't need full-blown SRIOV or SIOV because we're not using VMs. Right, so all we really need, basically it was, okay, try to standardize, go with something that's sort of standardized. So
Yeah, the reason I ask is for containers, not for the VMs.
Right.
We are trying to enable the SIV R1 right now. So if you guys need it too, that'll help because Intel is trying to get those patches in the VFIO subsystem. Can't remember the last question. It'll come back.
You can always come back.
You know it will be about PTP if you see me.
Yep.
But I'm curious how precise timestamping you require in your data centers, because usually you can get either all timestamps or precise timestamps. It's usually not together, especially on the TX side.
I'm trying to remember. Off the top of my head, I can't say what the precision is. I don't think it's that precise, though, as I recall. I know we're having to actually do a little bit of translation because if I remember right, I think we're passing back. I'm trying to remember how many bits the timestamp is we get. Actually, yeah. So we've got a timestamping expert over here. Oh, okay.
Yeah, all of them are precise. We carry the timestamps from the Mac, so they are actually wire side timestamping for all packets.
Mm-hmm.
Yep.
But it's
like nanoseconds, right? I don't know what the oscillator on the board is, but
yeah, that's not like the main question, because usually in the pipeline, in the file usually have its own, like, you know, caching, buffering, FIFOs or whatever, which also delays the transmission. And I'm curious if you care about this delay or just need a lot of timestamps that are.
That's the thing. The PHY is what's giving us our timestamps. So
3?
the PHY is, if I'm not mistaken, that's what's giving us our
I think it's
timestamps.
from the Mac, to be honest.
Is it the Mac?
Yeah, they pop out from the Mac, IP, right? But so this before PCS, but I think it's after the FIFOs inside the Mac.
Mm-hmm.
Yeah.
Okay.
And most devices, if you ask for all, give you the DMA timestamp, right? So this is the only device in the world. I mean, yeah, but you have to carry them through the pipeline back, which is not easy.
Yeah. The downside of asking a software guy about hardware stuff. Like,
do you carry them through like completions or?
Yeah, they come back through completions.
Okay.
So basically, if we issue a timestamp, we either have to get back a timestamp or we get a notification that the timestamp went horribly wrong and we won't get it back. That was a requirement we had to put on the hardware team. So it's like, yeah, no.
We're not hardware.
Yeah, we don't want to have to try to deal with reordering timestamps. So it's like, if it fails, just give us a failed timestamp and we'll just advertise it as failed.
Okay.
Question, does Meta intend to open the hardware, maybe push it in OCP?
There has been discussion of that. I think that might be more of a, well, that's the thing, is I have to be careful about what I say, because that's the thing. And some of the stuff, well, to give you an idea, so I think it was Andrew called out at one point, oh, this looks like synopsis logic. And I'm like, I can't say anything. So I had to go issue a request. Can I say this is synopsis logic? And I can now, that's why I'm saying it. But it took like a month and a half to wait for legal to get the approval. And it's like, okay, and if you use our register set, you shall always use this header at the top of your file. It's like, So there's going to be some murky water in terms of if we're going to open source it. I get the feeling we'll probably have to go through some more legal approvals to get that finalized.
Okay, so just take it, you can take it one unidirectional as input. I think this would be great to open.
Oh yeah, and that's the thing, is I think we've been pushing for wanting to do that. If nothing else, we might see if we can just open our spec up at least.
Be awesome.
Yeah.
Just adding to that, PCS is now available because they've written it in a generic way. You can all use it. You don't have to re-implement it in your firmware yet again.
Well, that's the thing, is that I think I mentioned before, we did mess up and we went and remapped it. So the code will be correct. The register locations will be horribly wrong.
Maybe the next generation will fix it.
Yeah, that's the thing. That's why it's like one of the requirements I asked for. It's like, okay, you know that MDIO bus we had on the Mac that you guys didn't hook up to the PCS? Please hook that up. So at least then I can actually use the address space correctly.
Yeah, so what I actually go for was, you pointed out you have the BMC there, which is pretty unusual. Linux doesn't really have a good story at the moment for BMC and sharing the link. So I think that's another area you're going to hit problems in the future.
Actually, I already did. That's the thing. I don't know if you noticed in the patch set, I'm enabling Wake on LAN if the BMC is present in order to just get it to, okay, no, leave the link there. Don't tear it down, because I went to go test it and it's like, and my system's off the network.
Yeah.
It's like, okay, well, okay.
I would say that's the okay hack for the moment, but we need a real BMC story. How do you share the link between?
Right. Which essentially, it looks like most of the code's there because I can just cheat and use Wake on LAN. So it's just, ideally I want to do it without having to say that, oh yeah, this Netdev supports wake on LAN and then set an extra bit in the filelib. So. Yep.
Many of us are working on SIOV R2, and my advice is if you're going to use only for containers, don't try R1. Even though it sort of works, it's more overhead. Either do sub-functions or R2 to be future-proof.
Well, that's the thing, is it probably will just be sub-functions. I don't think for a container use case, we weren't going to go full SIOV or SIOV, but it was just one of those things where it's like, okay, there's this spec here that's already there, and we can just make use of parts of it and tear it apart and use the pieces we need.
Largely white paper quality in my mind, not a spec.
Yeah.
So look for, there are more changes happening in R2. It's coming.
Yep.
You should wait for it to be more wiser.
Is there any like pre-published version of it?
Okay, I'm thinking, Anjali, you have a 30-second question?
Okay. I know the standardization takes time. So if you're this container, my view is just stick with R1. You'll get what you need. Yeah, I differ from Parav. You said you will think about opening the interface. So right now, it's not an open spec. So you don't expect other, multiple vendors or anybody to support it. It's all, your own NIC.
Well, we expect multiple vendors to manufacture it for us. But yeah, otherwise, we're not expecting Mellanox or Broadcom to go conform to our NIC. That's the thing, is essentially at that point, like when we were actually trying to do the early implementation for this, a lot of feedback we got is, oh yeah, we can do this. It's going to be a front end sitting on top of ConnectX blah. And it's like, well, no, that's not what we want. We want the whole pipeline different. It's like, no. Yeah, we'll give you Thor X plus this on the front. It's like, no. So that's the thing is, yeah, rather than having just some front end shim, it's like, okay, we want to have the whole data path under our control.
Yeah, I'm sorry, I'm going to have to cut it off here. Right, I would like to listen to Alex for another hour, but thank you, everybody. Thank you, Alex.